Okay, we're still talking here, chapter 15, solutions. And we've been talking about, again, solution stoichiometry. And remember, any stoichiometry, if it's basic stoichiometry, gas stoichiometry, solution stoichiometry, again, they basically all follow the same sort of four steps. We always want to have a balanced equation. We always want to kind of convert whatever they kind of give us to moles. We also want to determine, is it a limiting reagent type of problem? Then we want to use our limiting reagent and do our mole to mole relationship. And lastly, take those moles to some other unit. So really it's sort of these same four steps. The main difference here with solution stoichiometry is we incorporate really molarity here and volume a lot. And again, I would say very commonly, as we will see, and we talked about last time, kind of step number two, instead of maybe doing grams to moles, which you may still do in a traditional sort of stoichiometry problem here. A lot of times we will use our molarity equation and again solve for moles, which will be liters times molarity. So that's a very common sort of second step here in solution stoichiometry. And then at the end as well, it's very common to kind of use molarity at the end here. Again, you may be asked to actually just solve for the molarity using the moles that you calculated in the stoichiometry part and the volume that was probably given to you. You may also, very common sort of ending is to figure out the volume of something, of a solution. So figuring out like liters, for example, which would be moles divided by molarity. Again, those are two sort of common endings. Once again, the moles here would come from your stoichiometry, and you most likely would be given the molarity in the problem. And again, kind of solving for volume at the end. Lastly, just a traditional ending like we've seen before, actually the other way around, taking our moles to grams using molar mass. Also a possibility in terms of an ending as well. Any questions on any of that there? All right, so we did one problem to end with, so let's do another one here, I think. All right, so we want to calculate the mass of white solid calcium carbonate that forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of 0.15 molar sodium carbonate. All right, so once you take some time here and work through it, again, follow those kind of basic four steps. Thank you. Balance the equation, convert to moles. Is it a limiting reagent problem? Mole to mole. And moles to some other unit. This case, calcium 4008, carbon 12.01, oxygen 16, I think. Okay, so let's take a look, see how you're doing. So once again, obviously we have a stoichiometry problem. So again, we're not really given the equation. We have everything in words. So as we talked about a lot of times, we want to just make sure, again, when we are writing the equations that we start with the correct formulas, then worry about the balancing. And then obviously we can get into the stoichiometry part of it. So in this particular case, we're going to take a little calcium nitrate, it looks like. And we're going to react it with some sodium carbonate. Again, you should be able to recognize this at this point as a double displacement reaction. So we're going to switch partners here, the two positive guys. Again, when calcium and carbonate come together, that is +2 and -2, which gives us CaCO3, also in the problem given to you. And obviously, when sodium comes together with nitrate, remember again, sodium is +1, nitrate is -1. So once again, the proper formula here is NaNO3. Again, you should not have extra 2's in that formula or anything like that. And again, you want to get the proper formula. Now that you have the proper formulas on each side, we could then balance. And it looks like in this case, perhaps we just need a 2 there, I think, and that should do the balancing. We could also think about which ones are solid, even though in the problem they told us that that guy should be our solid. Everybody else here, based on solubility rules, should be aqueous, as nitrate is soluble in everything, sodium is soluble in everything, and obviously both of those guys together is going to be soluble in everything. So really everything here, except for the calcium carbonate, would be a aqueous solution. Any questions on getting that equation there? All right, so now that we have the equation, we really want to convert things to moles, but we could also kind of use the information given to us to really decide the other thing that we always want to look at when we're doing a stoichiometry problem, which is it a limiting reagent problem or not? So when we look at this here, for the calcium nitrate, we have 25 milliliters of a 0.1 molar solution, and we also have 20 milliliters of a 0.15 molar solution here for our sodium nitrate. And again, remember that the way you could really determine if it is a limiting reagent problem is, can you get moles for each of them? And because we are given the molarity and the volume for each of them, we definitely could get to moles of each of these guys. And because we could do that, this again is going to be a limiting reagent type problem that we do have to figure out the limiting reagent as we go through it. So the second thing we want to do is we're going to get our moles. Once again, here, a little bit different than a traditional stoichiometry problem. We're not going grams to moles. We're going to, again, use the molarity and the volume to do that. A reminder as well, as we talked about, that when you're using volume and molarity by itself, you do need to convert to liters so you get the right things you're looking for. So if we do that there, we're going to convert our 25 milliliters into liters. So 1,000 milliliters is a liter, 0.025 liters. We'll do the same thing for our 20 milliliters, which will give us 0.020 liters. So our moles of calcium nitrate here will be 0.025 liters. Again, I'm going to use the molarity where I can see both of the units there, which are moles per liter. So we are going to turn that into moles per liter so we can see both of them. Now we can see the liters canceling out. And that's going to give us our moles here, which in this case is 0.025 times 0.1. Looks like 0.0025 moles of calcium nitrate. We're going to do pretty much similar calculation here for our other reactant. We're going to go moles of sodium carbonate, and that's going to be 0.02 liters. Again, converting that milliliters into liters. We're going to use the molarity of it, getting rid of the big L and using both of the units. Once again, here, liters will cancel, and that's going to get us here. Looks like 0.003 moles of sodium carbonate. As we talked about before, that basically is your kind of starting amount, guys. Since it is a limiting reagent problem, I'm going to do that calculation where I try to figure out how much of one of them I need to use up the other. Obviously, as we've talked about previously, you could also just do separate calculations and figure out how much each one will make in terms of their product. Get rid of some of this here. Here. All right, so I'm going to take the calcium nitrate and figure out how much sodium carbonate is needed. So sodium carbonate needed. And that again would mean that I would take my moles of my calcium nitrate in this case. And I'm again going to do a mole-to-mole relationship between our reactants, which is a 1-to-1 relationship. So 1 mole of sodium, I'm sorry, that is calcium carbonate. That's calcium nitrate, actually. Put it what it is. That is moles calcium nitrate. Cool. All right, so 1 mole of calcium nitrate is 1 mole of sodium carbonate. It's going to give me 0.0025 moles of sodium carbonate is needed. Again, we're going to compare that to how many moles of sodium carbonate I'm starting with, which is 0.003. So I do have enough. And that means here that the excess reagent is my sodium carbonate and my limit, my calcium nitrate. So now that I know calcium nitrate is my limiting reagent, I can now finish up the problem by using my limiting reagent here. So we'll use 30 moles of it, which is 0.0025 moles of calcium nitrate. I can now do this to my product, which is a 1-to-1 relationship. A lot of 1-to-1s here. That's kind of nice. 1 mole of calcium nitrate, 1 mole of calcium carbonate. That's going to get me 0.0025 moles of calcium carbonate. That again would be my theoretical yield in moles, but we are looking for grams here. So the molar mass of calcium carbonate is about, when you calculate it from the periodic table, 100.1 grams per mole. And continuing on here to figure out how many grams that would be, we're going to multiply by the molar mass here, 100.1 grams per mole. And that will get me, looks like about 0.25 grams of calcium carbonate. That'll be my theoretical yield. Obviously, this is step number 1. We did step number 2, figured out our limiting reagent, step number 3, and step number 4 there. Yeah. All right, so as you see in this case, we actually did fit in kind of like normal, kind of thinking moles a gram. But as I mentioned, a lot of times you may already back into the calculation as well. Let's talk about some solution stoichiometry problems where that is really happens a lot. And that's with a process that occurs a lot of times when we use acid-base neutralization reaction. If you remember an acid-base neutralization reaction, if you take an acid plus a base, it will give you two things. It will give you a salt plus water, and a salt, again, is an ionic compound. And if you went through, like we talked about when we were doing sort of net ionic equations, if you went through the net ionic equation for any combination of like a strong acid and a strong base, this again is really the reaction that is happening is the formation of water. And one of the procedures that we commonly kind of use to figure out things like what is the molarity of a solution, maybe what volume would be needed, is we do a process known as titrations. And we're going to do a bunch of titrations tomorrow, I think. I don't know about a bunch, but we'll do a few, at least tomorrow. We're going to do titrations. And titrations is really a process that is used to figure out some information about an unknown solution. So typically when we do titrations, you usually will have a known solution, and you typically will have a unknown solution. And really the purpose of the titration is to help us figure out something about the unknown solution. Again, that could be the volume, that could be the molarity, it could be the molar mass, it could be a wide variety of things, but there's something about that unknown solution that we do not know. In the case of a known solution, much like the name implies, you pretty much know everything about it. So for example, very commonly, you know the molarity of it, you know the volume that you use. So you have like pretty much all that information sort of given. With the unknown, like I said, maybe you don't know molarity and you want to figure out a volume, or maybe you know the volume and you're trying to figure out the molarity. So there's some differences that you know. So in a titration, we typically will add one solution to the other. You could actually do it the other way you want, but very commonly, we typically will add the known solution to the unknown, but really, like I said, you can kind of do it either way. And when we do this, for example, with an acid and a base, a lot of times, you know, we're kind of adding our known solution to our unknown. And a lot of times, if this guy was your base and this was your acid, we would continue to add until this reaction is complete. And typically, where this reaction is complete is what is known as the equivalence point. And typically, what we use to add a solution, as you can see in this little picture here, is a burette. And a burette's very similar to almost like that gas tube we use in the other experiment, very similar tube like that. It has a little spout at the bottom. As you will see tomorrow, and as we'll talk a little bit about today, when you use a burette, the volume actually increases as you kind of go out towards the bottom here, and you're dropping from the bottom. So when you read the scale on this, if you were again somewhere in this ballpark, that would be something like 1.5 milliliters rather than 2 point something. So again, it increases as you go down on the scale. Now, we typically use a burette, and we typically will titrate until we reach the equivalence point. And the equivalence point in an acid-base titration is the point where the moles of the acid will equal the moles of the base. And pretty much what that means is you got equal amounts of both reactants. Everybody's gone on the reactant side. So you're going to use everybody up on the reactant side, and there'll be really nothing sort of left there. Now, a problem that occurs is a lot of times these things are colorless. So, like, how do you know when you kind of hit that point? So, very commonly, when we do a titration, we do use an indicator to help us visually see that we have basically hit the end of the reaction. So, an indicator is a substance that basically will change color once you kind of reach the equivalence point. How indicators actually work are they work over actually a pH range. So, for example, the indicator in this particular one here is most likely phenolphthalein, and that'll be like the one you'll use tomorrow as well. And phenolphthalein is an indicator that is colorless in acidic solutions. It's also colorless in neutral solutions, but it turns a lovely shade of pink to super dark pink, depending on how good or bad you titrate, really, really dark pink, in basic solutions. And phenolphthalein, for example, works on a pH range of about 8.3 to 10 pH, and that's the basic pH range. And around 8.3 is kind of colorless. And then it gradually becomes super light pink to super dark pink as you get closer to 10. And when you do a titration like we're going to do tomorrow, the goal is to actually, in the case of phenolphthalein, try to go until you see the lightest color of pink that stays. So light that you almost got to put it up against the whiteboard or a white piece of paper to kind of see the pink color. You know, it's almost colorless, which is a tinge of pink, is ideally what you're looking for. This is actually a pretty good color on this side here. Not too bad. The reason for that is when you get near the equivalence point, and probably the titrations like you'll do tomorrow, and the pH at the equivalence point is probably like 8.6-ish or something, that ballpark. So you really want to kind of stay at this end of the range, which is really kind of colorless, but you still need to kind of see that pink kind of appear to know you're almost at that thing. Now, one very common thing that will happen, and we'll talk more about it tomorrow probably as well, is when people do titrations, the very common thing that people say is, I just added one drop and is like went from no color to super dark pink. And that happens a lot in titrations because basically as you get near the equivalence point, you're going to learn more about this in 1B, but if you made a graph of pH versus, say, volume of your base that you're adding in a typical titration, you'll get what is referred to as a titration curve. It'll look something like that. And your equivalence point will be somewhere in this ballpark. And the reason, if you think about sort of the indicator that you're using, which runs from a pH of 8.3 to like a pH of 10, and again, it's kind of colorless on this side and obviously getting pink as you go this way. When you look at the equivalence point, as you get near it, you actually go pretty vertical in terms of the pH change. So basically, if you go from here to here, you are going pretty straight up vertical. And what that means is in terms of the volume that you would be adding from the burette, there is not a lot of volume change that occurs in that area. And because there's not a lot of volume change, you could add one drop, but what really does change a lot is the pH changes a lot in that range. So you could be like over here at your equivalence point. You could be like over here just past your equivalence point. And what you're going to see is you're going to end up with a pretty dark color pink because your indicator just jumped pH a lot, even though you didn't really add a lot of. And sometimes that's why people will say, you want to the lightest color pink possible. And some teachers will tell you, oh, that's too dark pink. You should do it again. And the truth is, in a lot of cases, that's really not necessary to redo your titration because what you're really interested in is the volume near the equivalence point. So if you happen to miss it by a drop or two, you would be about here, and your equivalence point would be about here. Again, if you went vertically down, it's pretty much the same volume. There's not a big difference in the volume. So your calculation is not going to be all that bad if you miss it by a drop or two. The reason why sometimes teachers will tell you that's too dark, you should do it again, is they don't know how you do a titration. You may titrate like I did when I went to school. I just opened that thing up, let a bunch of it drop in, shut it. I'm all cool, dark pink. I'm going home in 5 minutes and we're done for today. And if you really overshot the equivalence point, you could find yourself way over here with the same pink color that you have over here. And now when you think about where your equivalence point is, you are very far away, and you're going to be very off in your calculation. So, if you doing a titration ever and it's like no color and you put like a drop or two in and then it goes really dark pink, you really shouldn't worry probably much about the color of it because you're probably fairly close to the equivalence point volume of what you need. If you're really not careful and you like opened up and a bunch of it went in, and you're not really sure how much kind of went in there, you maybe should redo it again because you may be really past the equivalence point. Any questions on that? Again, you'll see that tomorrow. Heck, you'll probably even say it tomorrow at some point. I just added that one drop. I don't get it. All right. So let's talk a little about titration problems. The good news on titration problems is pretty much still solution stoichiometry. So we still follow our normal steps here. So if we take a look at this here, we want to know what volume of a 0.15 molar nitric acid solution is needed to neutralize 45 milliliters of a 0.55 molar potassium hydroxide. This again is a strong acid. That is a strong base. So this is definitely going to be a acid-base neutralization reaction, which as we talked about previously is really just a double displacement reaction. So definitely stoichiometry going on here. So we got to roll with an equation. So once again, we're going to take our nitric acid. We're going to react it with our base. And again, you should recognize it as a double displacement. And even easier in these type of problems is you should also recognize what we talked about, which is you should always make water in this case, which means you should always have water coming out. And if you remember when we talked about this with types of reactions, the water always comes from the same spot. It's always the H from the acid, the OH from the base. That essentially is where the water always comes from. So that is one thing that you should always form. And then obviously our salt here is just going to be what's left over, doing a double displacement, switching those guys together. Potassium +1, nitrate -1 will give us potassium nitrate in this case. And again, and we have our water formed and our salt in this case, which again, nitric. At this point, we're going to roll through our stoichiometry, which is I have an equation. I want to make sure it's balanced, and I think it actually is in this case. So we are balanced in this case. So step number 1 is done. We also want to maybe analyze sort of what's given to us so we could kind of think about what type of problem we got to go after here. So in this particular case, we are looking for the volume of the nitric acid. We do have the molarity given to us, 0.15. Again, I'm going to convert it into moles per liter. We also, for the potassium hydroxide, have the volume of 45 milliliters. And we have the molarity given to us of 0.550, once again, moles per liter. So just looking at this, and I would say sort of problem, which in books are sometimes worded this way, like a neutralization type reaction. I would say in most cases, it's not going to be probably a limiting reagent type situation. In most cases, it'll just be a basic stoichiometry problem. I know that this is not a limiting reagent, really for the same thing. I can only get moles of this guy. I cannot get moles of this guy. So it is just a basic stoichiometry problem. So because it's a basic stoichiometry problem, we can roll right into step number 2, which is the only thing that we can convert moles into. And if we do that, we can get our volume that we need to convert to liters. And if we do that conversion, 0.045 liters, dividing by 1,000, we're going to use our molarity of our KOH, again with the both units showing, so we can see them. That way we know our liters cancel. And that's going to get us here 0.0450 times 0.55. Going to go 0.02475 moles of KOH. Now we want to kind of think about how can we get to the volume of the nitric acid. I know I got molarity involved, right? So if I think about the molarity of the nitric acid, I do have the molarity given to me. I am looking for the volume. So again, the one thing that we're sort of missing for the nitric acid to get to the volume is the moles. And that's really the purpose of the stoichiometry here is we're going to use the stoichiometry. And in this particular titration, the KOH would be like our known solution. We know the molarity, we know how much volume we used of it, and really our nitric acid in this case is our unknown solution. So here we're going to use the information from our known solution and stoichiometry to figure out the moles of our unknown solution. So we're going to go to the equation. We're going to do a one-to-one relationship between these two. And 1 mole of KOH is 1 mole of nitric acid. And that would be step number 3 there. And that's going to give us 0.02475 moles of the nitric acid. And that stoichiometry step allows me now to check off up here that now I have the moles of my nitric acid. And now I have really everything I need to answer the question of how much volume. So step number 4 here is we're going to take those moles, in this case, to volume. So I have my moles of my nitric acid. And once again, by just taking a dimensional analysis approach, I don't have to worry about rearranging this equation. I could just go opposites cancel. I want to get rid of moles. I'm going to use my molarity here as a conversion factor. So I'm going to, wrong molarity, I'm going to point to the right one there. There we go. The nitric acid's molarity. And we're going to use that as a conversion factor. Here we need moles on the bottom. So I'm going to put my moles of nitric acid on the bottom and my liters of nitric acid up on top. And that is the molarity used as a conversion factor. And we're going to divide by 0.150. And that's going to give me 0.165 liters of nitric acid, which if I want milliliters, once again, 1 liter is 1,000 milliliters. And that's going to give me 165 milliliters of nitric acid would be needed in this case. First off, any questions on that? Hopefully you can see it is the same kind of 4 steps that we did previously, just using molarity. You need to, when you're doing a problem like this, a titration problem, you do need to make sure that you are doing it with stoichiometry like we just showed here. This is the place where people, as I mentioned the other day, decide, oh, cool, M1V1 equals M2V2. I just want to roll with that. Do not do that. You will not get credit, yes? And in some cases, you'll get the wrong answer. In this particular case, this is one of the cases where you actually will get the same answer because it's a one-to-one relationship. If your acid and base is not a one-to-one relationship, you will get the wrong answer. So you should not use that equation when you're doing titration problems or solution stoichiometry problems, because you will not get full credit, even if you happen to get the right answer. You got to show the work with stoichiometry in this class and probably all the chemistry classes you take. So try not to use that equation for things other than dilutions, basically. Any questions on that there? Wow. All right, let's see. That's the one. Is that the one we just did? No, that's. Let's do this one then. Why don't you take this problem here? What volume of 0.355 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfate? Okay, so again, take a look and see how you're doing. Once again, we are looking for the volume of sodium hydroxide that will react with sulfuric acid. So once again, we do have pretty much a base and an acid. So that is going to hopefully get you to an acid-base reaction, which is a double displacement. And obviously, we got some stoichiometry going on here. So we're going to start with the equations. So sodium hydroxide, which is NaOH, will react with sulfuric acid. No hydro in it, so it has a polyatomic ion. I get rid of the ick, I put an H, so that's sulfate. Remember, all acids are hydrogen as the cation. So sulfate's -2, so H2SO4 here will be our acid in this case. Again, going to do our double displacement, but we should know we should get water just like before. And water, once again, is going to come from the H and the OH. That means that these two guys will come together to make the salt part. We again want to put it together correctly. So sodium +1, sulfate -2 means we need a couple of sodiums there to go with our sulfate in this case. First off, any questions on how we got to the equation? At this point, obviously, we can do nothing with an equation if it's not balanced, so we need to make sure we balance it. In this case, it is not balanced, so I believe perhaps a 2 there, maybe a 2 there. We'll do a little bit of balancing in that case. And now we have 2 sodiums on each side, 1 sulfate, 4 hydrogens on each side. So we are balanced, hopefully, and 6 oxygens, hopefully, on each side as well. All right, now that we have that, we can kind of analyze what type of problem we're dealing with. Here we are looking for a volume of sodium hydroxide. We do have the molarity given to us, 0.355 molar. Again, I'm going to turn that into usable units there, moles per liter, and can use it as a conversion factor. For the sulfuric acid, we got 125 mils as our volume, and we also have a molarity, 0.5 moles per liter. Once again, analyzing what we got going on, we can only, again, get moles of one thing, so it is not a limiting reagent problem. We don't have to worry about that. And like I said before, typically in titrations, they're not limiting reagent problems. So we're just going to continue on with our stoichiometry steps, which is we're going to convert that into moles. Once again, we do need to take our volume to liters. So we're going to divide by 1,000. That will give us 0.125 liters of H2SO4. We will use our molarity here as a conversion factor, 0.5 moles per liter. Our liters are going to cancel, and we will end up with here 0.125 times 0.5. We'll end up with 0.0625 moles of H2SO4. Once again here, like kind of normal, we're using stoichiometry to find really the missing piece that we need for our, in this case, sodium hydroxide. Again, for the sodium hydroxide, we know the molarity. We're looking for the volume. So we do need the moles. And again, that is what the stoichiometry part of it is for, to figure out our moles of it so we can actually calculate what we're looking for. So to do that, we need to go to the equation here after step number 2 and do step number 3, which is our mole to mole relationship. And from the equation, it is actually a 2-to-1 relationship here. And for every 1 mole of sulfuric acid, we got 2 moles of sodium hydroxide. Moles of sulfuric acid will cancel. We will end up with 0.125, looks like, of sodium hydroxide. That is good because now I have the moles of sodium hydroxide. I have the molarity of sodium hydroxide. I again could rearrange the molarity equation or not even worry about the molarity equation and really just use my molarity of the sodium hydroxide as a conversion factor. So I got moles on top. So I'm going to use the molarity of the sodium hydroxide, put the moles on the bottom, liters on top. Moles will cancel, and we're going to divide by 0.355. Looks like 0.352 liters of sodium hydroxide. Once again, if we want milliliters here, we could go 1 liter is 1,000 milliliters. And that'll give us 352 milliliters here of sodium hydroxide. And again, that would be obviously step number 4 there. Any questions on that one there? So for titration problems, this is sort of a common sort of ending. Again, let's take a look at one more here to finish up titration type problems that has a different sort of thing we're looking for. If we did a titration and it required 63.5 milliliters of 0.375 molar calcium hydroxide to reach the equivalence point in a titration of 95.5 milliliters of hydrobromic acid, what is the molarity of the hydrobromic acid in this case? So in this case, we are looking for molarity. So if it says something about titration, just like if it says anything about neutralization or reacting, and you got an acid and base involved, it's definitely a solution stoichiometry problem. And calcium hydroxide is a base, and obviously hydrobromic acid is an acid. So once again, we do have that acid and base sort of thing happening here. So we want to again start with the proper formulas. Calcium being +2, hydroxide being -1 means we need 2 hydroxides in this case, plus hydrobromic acid. That's going to be HBr. Again, remember that hydro are acids that do not contain oxygen, so it's just basically a hydrogen and a halogen probably. And again, we're going to get our normal sort of water formation here, which again is the reason why this sort of reaction takes place. H and OH coming together to make water. That leaves our calcium and bromine to come together. And once again here, we do want to make sure we get the right formula. So calcium again being +2, bromine, our bromide being -1 means CaBr2 is going to happen in this situation. Once again, we have our equation. Now we need to do a little bit of balancing here. So maybe a 2 there and also a 2 there, I think, as well. We'll do it. We got 4 hydrogens on each side, couple of oxygens on each side, couple of bromines, and a calcium. So we're good. Once again, now we could kind of roll into the stoichiometry part of the problem. We're going to kind of identify what's given to us. So in this case, we got 63.5 milliliters of a 0.375. Once again, I'm going to turn that into moles per liter. So we have the molarity and the volume given to us of the calcium hydroxide. Here we're actually looking for the molarity of the HBr, which would be moles per liter. So we're actually looking for that. And we do have the volume given to us, which is 95.5 milliliters. So we're looking for the molarity. We have the volume given to us. Once again, here we are going to use stoichiometry to get the moles so we can figure it out. And again, very common here. It is not a limiting reagent problem. Once again, only could get the moles of one thing. So we will get to the moles of the calcium hydroxide here. Again, converting our volume into liters will give you 0.0635 liters. We're going to multiply it by the molarity of our base, moles per liter of our calcium hydroxide. That's going to get us here 0.0635 times 0.375. Looks like 0.02381 moles of calcium hydroxide. That being our second step, and this being a non-stoichiometry problem. We're now going to do mole-to-mole relationship. It's a 1-to-2 relationship between our base and our acid. So using our stoichiometry relationship there, 1 mole of calcium hydroxide gives us 2 moles of HBr. That's what's going to allow us to get to the moles of the HBr, which is what we're looking for. And if we do that there, it looks like we're just going to times it by 2. We will end up with 0.04763 moles of HBr. By using stoichiometry, we now have the moles of our HBr. We were given the volume of HBr here, so we can now find the molarity. We do want to be careful here. Again, molarity is moles per liter. So our volume of HBr that was given to us, we do need to convert into into liters. So we have the right answer, and that will give us 0.0955 liters. That is what we want to divide this by. And again, now nothing's going to cancel in this case. So we'll divide by 0.0955. And that's going to give us here. There we go. Let's try that again here. There we go. I had an extra 0 the first time. All right, so 0.49, we'll call it 9. And again, the units don't cancel, so you can leave it moles per liter of HBr. You could also, like we talked about, kind of incorporate the big M at this point of HBr in terms of your answer. And again, this is our fourth step. We're actually finding the molarity in this case. Again, a very common ending for titration problems. Very commonly, you do titrations to figure out the molarity of your kind of unknown solution, either your acid or a base. It's a very common sort of calculation, and one you'll do tomorrow, actually. Yes. Any questions on that? Yeah. Yeah. What's questions? I don't know. When we take a break, I'll look at it. I don't have no question on top of my head. Other questions? All right, questions on titration problems, which again are solution stoichiometry problems. Just again, one more final note about the M1V1 equals M2V2 equation. If you use it on this problem or you use it on the previous problem, you will get the wrong answer. So again, do not use that equation for this type of problem. Do the stoichiometry and show the steps so you'll get the right answer and get all the credit as well. Any questions on that there? All right, normality we are not going to talk about, so don't worry about that part of the chapter. That means this is chapter 15, and we're done with that chapter. We'll take a break, and we'll hit chapter 16, which is second to last chapter. Can't be bad, I guess. In this chapter, we're going to talk obviously about acid and bases, the pH scale, and how to calculate all that stuff. So let's start with just some basic sort of ideas about acids. Acids are first recognized by their sour taste. There's some acids that we see a lot. Vinegar, which the main component there is acetic acid, citric acid there in lemons. Bases, on the other hand, are characterized by a bitter taste, and they oftentimes feel very slippery. A lot of hand soaps, drain Drano, that type of stuff, unclogging solutions are basic. A lot of bases are referred to as being alkaline or alkalized. And as we probably talked about previously, if you look on the periodic table, group 1, which is the alkali metals, group 2, which is the alkaline earth metals, that is where a lot of our really strong bases come from. Those kind of 2 groups on the periodic table that essentially have hydroxide with them. Now, sort of an early definition of an acid and base was one done by Arrhenius. He did a lot of work with electrolytes, and if you remember, electrolytes are those solutions that break apart into ions in solution. And he defined an acid as something that has the ability to produce hydrogen ions in solution. And hydrogen ions are H plus. And again, when we're talking about an acid, what we're talking about is, again, something that has the ability to produce free floating H plus ions in solution. Again, not really attached to anything, just kind of floating around freely in the solution. Also, one of the things that you should understand about acid-base chemistry is we use sort of some different symbols along the way for acids. H plus, which is the hydrogen ion, is the same as H3O plus and used interchangeably in acid-base chemistry as a polyatomic ion known as the hydronium ion. So if you see H plus or you see H3O plus, it basically is the same thing. It basically means the acidic part of the solution or the acid part of the solution. Now, in addition, as we will later see in a second, H plus, which is the hydrogen ion, is also sometimes referred to as a proton in acid-base chemistry. And again, hydrogen, which has 1 proton and 1 electron and no neutrons. In order for it to become positively charged, it had to lose its electron and only has a proton left. So very commonly as well, H plus is referred to as a proton in acid-base chemistry. Now, you may be asking, like, what would be the difference? And really the difference is a lot of times how you sort of write an equation and what ends up happening when you write that equation. So if we had an acid like hydrochloric acid, for example, which is a strong acid and also a strong electrolyte. And what that means is when hydrochloric acid is in water, it is basically going to completely break apart. So you could, for example, show the dissociation or breaking up of hydrochloric acid in an equation such as this, which is very commonly done, where we just write hydrochloric acid and breaks apart into H plus and Cl minus. And that's perfectly acceptable, very commonly done. A lot of times nowadays, books and stuff will show in the equation water, and that you're kind of dissolving it in water, and they will include water on the reactant side of the equation. And when they do so, what they will form is H3O plus and Cl minus. And again, these 2 things are basically equivalent to each other. What happens in this case, as we'll talk about, is basically the H plus heads over there to the water, and the water picks up the H plus in this case. And you could use H plus or H3O plus. I will say books and stuff typically like to use H3O plus these days. I typically like to use H plus because it's just what I've used long years. But again, anywhere I put kind of H plus in formulas or equations, you could basically substitute H3O plus in there for the same thing. Now, when we talk about a base is something that can produce hydroxide ions, so OH minus, and very much like our acid, what we're talking about when we talk about a base is something that has the ability to produce those free-floating hydroxide sort of ions in solution. Obviously, as we'll talk about the relationship of how much H plus you have in the solution versus OH minus, will also help us determine whether or not the solution is going to end up being acidic, basic, or maybe even neutral in a case. Now, Arrhenius did a lot of work with acids and bases and electrolytes, but he did a lot of work with sort of bases that had hydroxide on them. And here, as we can see, sodium hydroxide will have hydroxide on them. And not all bases will actually have hydroxide in the formula. Some bases will not have hydroxide in the actual formula. An example of that would be ammonia. Ammonia, again, is a weak base. And when ammonia is in solution with water, what will typically happen is the ammonia will actually grab an H plus off of the water and it will form NH4 plus, which is the ammonium ion, one of those polyatomic ions, and it will form hydroxide here. And the formation of hydroxide is what makes ammonia a base. It's a weak base because it's a weak electrolyte. And if you remember when we talked about weak electrolytes, we had those two arrows heading in both directions. And that's the case here. And that is why, for example, ammonia is a weak base versus sodium hydroxide, which is a strong base, because when sodium hydroxide goes for a swim, it pretty much has the hydroxide on it. It's just going to release it into the solution. Ammonia has got to go find some water molecules, do a little reaction to kind of produce the hydroxide. So something like sodium hydroxide is going to produce a lot more free OH minus in the solution a lot faster than ammonia will. And that's going to make it a much stronger base. Speaking of sort of strong acids and strong bases, a couple of reminders. We talked about a list, and we'll see it probably as we continue through this chapter a little bit more. Again, there's a list of strong acids, which is a good one to know. Hydrochloric acid, perchloric acid, sulfuric acid, nitric acid, hydrobromic acid, and hydriodic acid. That's again a list of 6 strong acids that will completely break apart in a solution. And it's a good list to know. In terms of your strong bases, as I mentioned before, group 1 and group 2 on the periodic table. If you start where like lithium is, you hang down there to sodium, potassium, make a right-hand turn over there to calcium, and a few of those underneath is strontium and barium. If you hook up any of these guys, for the most part, from group 1 and 2, with hydroxide, like lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth, that's where a lot of your strong bases come from. So a lot of strong bases come from group 1 again, and 2 on the periodic table is pretty much where a lot of those strong bases come from. Most weak bases, as you'll come across, and again, probably not too much in this class, but most weak bases will kind of look like ammonia. A lot of them are organic type bases. They have like that nitrogen, some hydrogens on them, and some carbons and stuff like that. And that's where a lot of like weak bases sort of look like. Now, the concept was really good, as I mentioned, but it did only kind of focus on bases that had hydroxide in the formula. So, a more sort of general definition of acid and bases as commonly used is what is known as the Bronsteed Lowry definition of an acid and a base. And in a Bronsteed Lowry definition of an acid and a base, an acid is a proton donor. That means that the acid will give away an H plus. It is important to remember that it is not just the hydrogen, but the plus is important because the plus changes the charges on things. So when somebody loses a positive charge, like an H plus, they become more negative. When somebody gains a positive charge, they become one less negative. So you want to make sure you adjust with the charge as well. A base is something that will accept an H plus along the way. So if we think about the two sort of formulas, reactions that I put up there, if we took the hydrochloric acid and actually showed the water in the equation, we will get H3O plus and Cl minus. There we go. And what's going to happen here is the HCl is going to donate its H plus over, and that would make which makes a lot of sense that the hydrochloric acid is my acid. Water, by the way, in this case, is acting as the base. It is the one that's accepting the H plus when it comes over. And if you take a look at that sort of weak base one we looked at with ammonia, NH3 plus our water, NH4 plus, and OH minus. And in this case, the water is going to send the H plus over. And in this particular situation, it is the water that's actually the acid, and the NH3 here is going to act as the Bronsteed base. And again, what we see here is something that does happen. In the first example up on top, the water was acting as a base. In the example on the bottom, the water is actually acting as an acid. And things can act as an acid or a base, and that is what is known as amphoteric substance. So an amphoteric substance is something that has the ability to act as an acid or a base. Water is a very common thing that can do that, and a lot of things that you'll see that has a hydrogen and a negative charge also has the ability to do that. So this is a classic sort of Bronsteed Lowry definition of an acid and a base. And also, again, if you kind of write the equation in the Bronsteed Lowry definition, you will produce that H3O plus rather than just the H plus. Now, another sort of consequence of the Bronsteed Lowry sort of definition is that we do create partners on the other side of the arrow. So on the left-hand side here, HA is my acid. It's going to donate the H plus over. And this guy is going to be my acid. That means water here will be my base. And it will actually create two things on the other side that are related to those things. On the right-hand side, it will create the conjugate acid. And on this side here, it will be our conjugate base. So the relationship between the left-hand side and the right-hand side in this Bronsteed Lowry definition is the acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other side. Now, we always find, for example, regular old acid and bases, left-hand side of the arrow, your conjugate acid and bases on the right-hand side of the arrow. So your conjugate guys should be on the right-hand side of the arrow, your acid and base. Now, also a really important relationship between those two things is this: the absolute only difference that there could be between, for example, the acid and its partner conjugate base, or the base and its partner, the conjugate acid, the absolute only thing that can be the difference between those two things is this guy right here. It can only be a 1H plus difference. If you have something that may look very similar, but the difference is more than 1H plus, they are not Bronsteed Lowry conjugate acid bases. It could only be 1H plus difference between them. And when we look at the acid to our conjugate base, it has one less H plus because it gave it away. And when we go from the base to the conjugate acid, it has one more H plus because it accepted it. So that is, again, a really important thing to keep in mind, that if you're asked, are these things sort of related to each other, it has to only be a 1H plus difference. Any other differences, then they are definitely not related to one another. If we go back to sort of those formulas I wrote a bit ago here, if we take a look at these things, we could see the relationship, the Bronsteed Lowry relationship, when we look at these guys here. And again, we'll get rid of some of this here. All right, so over here, obviously, we had our acid and our base. And on the other side here, this is going to be our conjugate base. And this is our base. And on this side here will be our conjugate acid in this case. And again, it is just a 1H plus difference. one less H plus, and it is basically this H plus that's being given away. So this guy shoots over here. And when we look over here, it is one H plus difference between this guy and the other side. Again, it has gained that H plus along the way. So it has one more H plus, as I mentioned before, that it started with. On the bottom one here, again, this is going to be our base. This will be our acid. On the other side, our base is related to something that looks like it, and that would be our conjugate acid. And our acid would be related to our conjugate base here. And again, the only difference is that one H plus that is heading over there from the water to the NH3 in this case. Any questions on those relationships? So as I mentioned previously, again, one H plus difference gives us those pairings that occur. And if you again write sort of an acid dissociating, kind of showing the Bronsteed Lowry definition, that is where you will produce that H3O plus. As I mentioned a second ago, this is really just the strong acid breaking apart in water, which can be simplified and just written like so, where we don't include the water on this side and we end up with H plus. Again, those are basically equivalent sort of equations for what's happening, and all that's really happening in this case is your acid is basically breaking apart in water. And there we got going on there. And again, that is our hydronium ion there. And that's our H3O plus. All right. There we go. So for each of these, we want to know which ones represent a conjugate acid-base pair. So take a moment for each of these and see which ones are related to each other by the Bronsteed Lowry definition. Really, when we're trying to determine if they are related to each other, this is pretty much what we want to think about. Is that the only difference? Is basically, and again, that could be the only difference between those two things. So if we take a look at HClO4 and ClO4 minus, the only difference between this is an H plus. You can either put the H plus on the guy on the right and you get the guy on the left, or take the H plus off the guy on the left, you get the guy on the right. So I would say yes on that. We take a look at the second one here, HCl and ClO minus. The difference here is an H plus, but there is also a difference of oxygen that is not in one of them, but is in the other. And because of that, that will not be a pair, even though they kind of look very similar to each other. We take a look here. H2PO4 minus and HPO4 2 minus. The difference here is 1H plus. So when we get rid of the H, we're left with just 1H on the left. And remember that when you lose a positive, you become one more negative. So that -1 becomes a -2, and they are related to each other. So again, that positive charge does change the charges on other things when they are gained and lost. Lastly here, HNO3, NO3 minus. Once again, the difference here is 1H plus between those two. Once again, if you get rid of the H on the left, you're left with NO3, and it was neutral and lost the positive, becomes one more negative, and again, you end up with the guy on the right. So it does look like it is 1, 3, and 4 here that are pairs, and obviously number 2 is not a pair. Any questions on that? How about this one? H2SO4 and SO4 2 minus. Are those guys pairs? The answer is no, they are not pairs, even though they look alike, because the difference here is not one H plus. This is a difference of two H pluses, which again is too big of a difference for them to be pairs. Now, why is that? That is because when we look at sulfuric acid here, this is what is known as a diprotic acid. It has basically two hydrogens to give. That's different than, say, HCl, which is known as a monoprotic acid. It has one H plus basically to give, mono being one, or even H3PO4, which is a triprotic acid. Now, when acids actually lose their hydrogen, so when they give away their hydrogens, it actually does not all happen at once. So even though we kind of wrote an equation in the last chapter where we had H2SO4 and it kind of gave away both hydrogens, it actually doesn't happen all at once. It happens in a stepwise fashion. So what actually will happen first is that H2SO4 will lose one hydrogen and make HSO4 minus. Then that HSO4 minus will lose a second hydrogen and make SO4 2 minus. So it actually happens in sort of a stepwise fashion. And that is why, for example, if we were looking at pairs, this guy here and this guy, these guys are pairs. They're only one difference apart, H plus apart. This guy here and this guy here are also going to be pairs because they are only one H plus difference apart. But again, if we try to jump kind of straight from here to here, they are not going to be pairs again because it's basically two steps down the road and two H plus differences. Any questions on that? By the way, you might be able to imagine, do you think it is easier to remove the first hydrogen or the second? Which one should be easier? It is definitely easier to remove the first hydrogen. It's neutral. So when you get rid of that first hydrogen, you now have something that's negative. So it's much, much harder to remove the second hydrogen. And for example, if you had three hydrogens like you do in phosphoric acid, it's like really hard to remove that third one as well. And in reality, most of the hydrogen that comes off actually is the first hydrogen. So that's the one that's going to release probably most into the solution. Very little the second hydrogen. And again, in the case of phosphoric acid, if you have three hydrogens, it would be very little as well. All right, so for each of these, write the formula for the conjugate base. So if you're starting with each of these, write the formula you should get for its partner, the conjugate base. Okay, so let's take a look, and hopefully at this point you understand that really it is just an H plus. The key that most people struggle with is like, should I put it on or take it off, right? Is sort of the question. So this is where understanding the relationship that we've been talking about in terms of, on the left-hand side of the arrow, you have acid and a base, and on the right-hand side of the arrow, you have a conjugate acid and a conjugate base comes into play. The relationship is, as we talked about, the acid on this side is related to the conjugate base on that side, and the base on this side is related to the conjugate acid. So what that means is when you come across a question like we have here, which is they want you to write the formula for the conjugate base. So they basically want you to end up over here, which means if you think about it backwards, where you're starting from is way over here. And that means that every one of these things is an acid in this case. And at this point, all you have to do is use the Bronsteed Lowry definition of an acid, which is an acid should donate an H plus, right? And that's what an acid should do. And that means for each of these, we should take off the hydrogen ion. And that's how we could kind of figure out what we're left with. So if we start here, we're going to take off a hydrogen. It leaves us one hydrogen and a sulfur. It was neutral to begin with. So as I've been talking about, the positive charge is important. So when you lose one positive, you become one more negative, and you do end up with HS minus as the formula here for our conjugate base. Now, starting with HS minus, we're again going to lose a hydrogen, which means I shouldn't write hydrogen there. We're going to lose the only hydrogen that we got left. And obviously at this point, we started with a -1. We lost the positive charge, so we become one more negative. So we go from -1 to -2, and we end up with S2 minus in this case. Any questions on those two there? Same thing down here. We know that all this guys are going to act as an acid. We're going to get rid of a hydrogen. Leaves us a nitrogen and 2 hydrogens. Once again, though, we did start as neutral, which means when we lose the positive charge, we become one more negative. We do need the negative charge on top of that. And lastly, going to lose a hydrogen, leaves us one hydrogen, SO3, and going to become one more negative, which will give us HSO3 minus. So if you understand that relationship, and I'll be honest with you, a lot of questions, they won't just straight up come out and tell you, hey, these are acids or these are bases. They will just simply ask you, like it is in this question, write the formula for the conjugate acid or write the formula for the conjugate base. So again, if you're not sure what you're starting with, you kind of think about it sort of backwards and just go by the definition of the Bronsteed Lowry acid or base. Any questions on that? So if we had something like, say, our HCO3 minus, what would be the conjugate acid? And what would be the conjugate base? So once again, I'm going to start with the conjugate acid. And in this case, if I'm not sure, I know I want to end up here. And I know the relationship is if I go back to the other side, that means that thing is going to act as a base in this case. And once again, the definition of a base from Bronsteed Lowry is it should accept the H plus. That means I'm going to, as I'm going this way, I'm going to add the H plus basically to it. And if I do that, I will put an H on there. That gives me two H's, a CO3. Plus 1 minus 1 gives me 0 charge, and I get back to carbonic acid in this case. Yeah. Now, if I'm going the other way, very similar to the problem we did here, I want to end up as a conjugate base. So again, following it back over, going to tell me it's an acid. So going in this direction, I'm taking off that H plus. And again, I'll be left with just a CO3. Started at -1, loses the positive, becomes one more negative, and I end up at carbonate in this case. Questions on that there? This is another example, as you can see, much like water, of something that can act as an acid or a base. It is amphoteric. I will say most things that you come across that have an H and have a negative charge has the ability to act as an acid or base. Like this guy right about there can do both as well. He could do that. And also like HSO4 minus that we saw earlier has an H to give. And because it has a negative, it could also accept it. So a lot of times if you come across any of those things with like a hydrogen and negative charge, it does have the ability to act as an acid or base and can be amphoteric. Good news is for our class, not that important. But when you get to 1B, when you talk about salts, you'll see that a lot sort of happening. Any questions on conjugate acid-base pairs? So you need to be able to identify them, need to be able to, like this question, write the formulas for a conjugate acid-base pair. By the way, if you're asked that question, your answer should look something like this. Should just be one thing, not like a whole entire equation or anything like that. Yeah, so it should just be like one formula written. All right, so as we've been talking a little bit about acids, and obviously we touched upon acid strength as well. If the forward reaction of the acid reacted with water when it dissociates, the products can recombine and go in the other direction and create more of a weak acid. And if that sort of forward direction predominates, then you're definitely going to get a strong acid. And once again, a strong acid is a strong electrolyte, which means it's going to completely 100% break apart in solution. You will have none of the whole units together. So just like we talked about with strong electrolytes, strong acid is the same. So as we talked about, if you had hydrochloric acid solution, if you were to look in that beaker, you would have nothing but H pluses floating around and Cl minuses floating around. Once again, because it's going to completely break apart, you're going to be able to create a lot of H plus in that solution really quickly. And that again is why it's considered a strong acid. All it has to do is go for a swim, and it's going to release that H plus into the solution, and it's going to have a much higher H plus concentration in that solution, making it very, very acidic, most likely. Again, you will have none of those kind of HCl units together. That list I put up on a couple of slides ago and a couple of times throughout the semester, again, those strong 6 acids is a really good list to know. As we talked about maybe previously, again, just by process of elimination, if you come across an acid and you can recognize something as an acid and it's not one of those 6, you could probably safely assume that that's going to be a weak acid. So it's a good thing to kind of know. Speaking of weak acids, if that sort of reverse reaction sort of predominates, you're going to get a weak acid. And again, that typically will have those arrows heading in both directions. And the difference is, for example, if you took something like HF, which is hydrofluoric acid, by the way, I know that's a weak acid because it is not one of those 6 that we had on the previous slide. When you dump that into solution, you will actually mainly have HF units still together. It will break apart a little bit into ions and will produce a little bit of H plus in the solution. Since it's still able to produce a little bit of H plus in the solution, it is still considered an acid because it has the ability to basically produce that. But it's nowhere near as strong of an acid as something like HCl that's just going to release all of its H plus into the solution and create a lot more free H plus in that solution. So HF, which is a weak acid. Weak acids are weak electrolytes, which, as we talked about with electrolytes, they pretty much stay together when they go for a swim. They break apart a little bit, but they mainly stay together. And because they mainly stay together, pretty much that guy's going to hold on to his H a lot more than something like a strong acid that's not going to hang on to his H all that much. Now, some relationships that not super important for perhaps this class, but again, when you get to 1B, you will see it a lot more. The relationship between an acid and its sort of conjugate partner, its conjugate base, is sort of an opposite relationship. And what I mean by that is if you have an acid on one side of the arrow and its partner on the other, which is the conjugate base, if that acid is a strong acid like HCl, its conjugate base will be relatively weak, like Cl minus. If you have a weak acid on the left-hand side, like HF, its conjugate base will be relatively strong, like F minus. Now, when we talk about sort of weak or strong in terms of its conjugate partner, what we're really talking about is something that we don't get too much into in this class, but what it basically means is if you have a salt, and that's pretty much where these guys will end up. If you remember, we make on the right-hand side a salt and water, basically. That salt that contains that Cl minus, that Cl minus is considered a neutral salt because it's weak. And what that means is it will not continue to react. If you have a salt that has like F minus in solution floating around, that's relatively strong. And what that means is that F minus has the ability to actually keep reacting with the other thing that's in the solution, which is water. And it could go through a reaction known as a hydrolysis reaction, where the F minus will go find some water that's in there with it and actually will take an H plus from the water. The result of that is you will make HF, and more importantly, the result of that is you will actually make some hydroxide in that solution. And it will actually turn that solution into a basic solution because this F minus has the ability to continue to react, basically. In this case, it's actually acting as a base, right? It's accepting the H plus from the water. It is not strong, though. For example, it is not a strong base at all. It's just strong in the sense that it has the ability to continue to react. This reaction, again, is what is sometimes referred to as a hydrolysis reaction, which we definitely don't cover at all in this sort of class. But it does have that ability to do that. Same thing with our base. If you were to look at the base on one side versus the conjugate acid on the other, if you had a strong base like sodium hydroxide, it will have a weak conjugate acid, which in this case would most likely be the sodium. And if you have a weak base, like ammonia, it will have a relatively strong conjugate partner, which in this case would be the ammonium ion. Same thing, the ammonium ion, for example, can continue to react with water, and it will actually produce H3O plus and make the solution more acidic. If you have something like ammonium chloride solution, should be an acidic solution because that HNO3, that NH4 plus can react with water and donate the H plus over, and it will make NH3 and H3O plus, which again will make the solution more acidic in this case. Now, that's just a relationship between those two. That's all you really have to know for our class is just a relationship of if it's a strong acid, its partner will be weak, and if it's a weak acid, its partner will be strong. You don't have to obviously do the equations or anything like that, but that's essentially what's happening here. By the way, the sodium here would also be a neutral salt. It will not do any reaction with water. That is why, for example, when you have a solution of sodium chloride, it should have a pH of 7. It should be neutral because you basically have just sodium ions floating around chloride ions, both of which will not react with water or do anything to mess up the pH of the solution. We talked a little bit about it earlier. Again, there are certain acids that are strong acids that are good to know, and some that can donate more than one hydrogen. Again, it's going to come off one at a time. Monoprotic means one hydrogen. And by the way, in terms of acids, you also will sometimes see a generic symbol like HA. And that's a generic formula for a monoprotic acid. It has basically one hydrogen to give. You may see something like H2A written, and that's a diprotic acid. And you may see something like H3A written, which is a generic one for a triprotic acid, which has 3 hydrogens to give. Real life examples of each of those: HCl, H2SO4, and H3PO4. Real life examples of sort of those generic sort of formulas. And the A's in each of those formulas do have the different charges. So sulfate has a -2 charge, phosphate has a -3 charge, and that's why we have 2 hydrogens in the second guy and 3 in the last guy. Any questions on that? All right. So as we talked about, there are certain things that can act as an acid or base, which are amphoteric. And a couple examples that we saw with water, again, in the first case here, water donating the H plus, becoming an acid or acting as an acid. In the second case, accepting the H plus, acting as a base. Water can even react with itself, where one water is the acid, the other is the base. It's pretty much what's happening in a water solution all the time. So if this was my acid and this was my base, this water would send an H plus over and would create H3O plus and OH minus on the other side. This is a reversible sort of reaction. It is arrows heading in both directions, which is what that arrow is supposed to represent. And that sets up what is known, for example, as an equilibrium. And an equilibrium we'll talk a little about in the next chapter, but for the purposes here, this sets up a relationship which is useful in acid-base chemistry, which is known as the Kw relationship. And the Kw is the equilibrium constant for water, hence the W part of it. And the Kw is equal to the concentration of H plus times the concentration of OH minus. And most of the time you will use this form number here. That equals 1 times 10 to the minus 14. By the way, when we do see the little bracket, that again is typically meaning concentration. And typically that means molarity. Moles per liter is what goes into there. This is one of those formulas, as I mentioned before, that if you don't want to use the H plus, you will most commonly see it the H3O plus and the OH minus will equal 1 times 10 to the minus 14. This again, both of those things are the same thing. The H plus concentration are the H3O plus concentration. They are equal to each other, and they basically represent the acidic part of the solution, while the OH minus represents the basic part of the solution. And that number of 1 times 10 to minus 14, you can pretty much assume it as a constant. It is, again, a value kind of like the R value, which is usually never given to you in a problem, but it is, again, a value that you always kind of have available to you. So usually never, ever mentioned in a problem. But again, that relationship is usually there. It does change, by the way, not important for our class, but it does change with temperature, but pretty much 99.999, almost 100% of the time, that's going to be the number that you're going to roll with it. What can we do with this? Well, what we could do with this relationship is if we know the concentration of the acid part of the solution, the H plus, or if we know the concentration of the basic part of the solution, the OH minus, we could actually calculate the concentration of the other and compare the two to help us determine whether or not we have an acidic solution, basic solution, or a neutral solution. And the relationship between those two is as one goes up, the other goes down. So the more H plus you have, the less OH minus you have in the solution, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. So one goes up, one goes down. And again, like I just mentioned, the concentration or relationship of how much H plus to OH minus you have in that solution will tell you if the solution is acidic, basic, or neutral. The good news is it really is the same calculation regardless of which one you're doing. You're basically going to take 1 times 10 to the minus 14 and divide it by the other concentration, and that will give you the one you're looking for. So if you have the hydroxide concentration, 1 times 10 to the minus 14 divided by it will give you the H plus concentration, and vice versa. If you have the H plus concentration, or again the H3O plus concentration, which is the same thing, you could calculate the hydroxide concentration. If you do that and the H plus, which is the acid part, is bigger than the base part, your solution is going to be acidic. If you calculate it and the base part, the hydroxide part, is bigger than the acid part, it's going to be a basic solution. And if you calculate and they equal each other, they will both equal 1 times 10 to the minus 7. It will be a neutral solution. So you can compare both of those things. We do bring up in this chapter for sure a calculator alert. Yes, you definitely want to make sure you're using your exponent button. Otherwise, you're going to be, well, screwed in this case. You're going to be off on your calculations along the way. You definitely want to make sure you use that EE button, the EXP button when you're punching these in. And you'll know really quickly that you're probably off when you start checking answers. And usually what will happen is the front part is all good, but the exponent part's off by like 1, and it's probably how you're punching it in. So you just want to make sure you punch it in properly using your exponent button in proper scientific notation. All right. So with that being said, let's give some tries here. Each of these are separate problems. For each of these, calculate either the H plus or OH minus concentration, depending on which one's given to you, and then determine are they acidic, basic, or neutral. It is, again, using that KW, which again is our H plus concentration, our OH minus concentration. Again, it equals 1 times 10 to the minus 14. So in the case of the first one, we are given the H plus concentration. So we will be looking for the OH minus concentration, and that's going to be 1 times 10 to the minus 14 divided by our H plus concentration, and that will get us here divided by 3.4 times 10 to the minus 4. And again, making sure we do use our exponent button. So 1 exponent button, negative 14 divided by 3.4 exponent button, negative button, and 4, look like. And that's going to get us here a 2.9 times 10 to the minus 11. The units here are molarity, and it is a concentration, so it does need units. First off, any question on that calculation there? We now want to compare the H plus concentration to the OH minus concentration. So in this case, when we look at it, our H plus concentration to our OH minus concentration, our H plus concentration is to the minus 11. Our H plus concentration is to the minus 4. That means the H plus concentration is larger than the OH minus concentration, and this solution should be acidic. First off, a reminder that when you are comparing exponents, the negative is kind of important, yes, because when you look at this guy that is 3.4 times 10 to the minus 4, you're just going 4 places this way and putting zeros. But when you compare it to the other guy, which was 2.9 times 10 to the minus 11, you're going way more to the left there and putting a lot more zeros, making it a much smaller number. So when you're comparing negative exponents, the actual smaller negative exponent is the larger number. Yeah, so that's a good thing to keep in mind. Sometimes people get a little confused on that. Looking at number 2 here, same deal. We have the H plus concentration, so we could calculate the OH minus concentration. We're going to take 1 times 10 to the minus 14 divided by our H plus, 2.6 times 10 to the minus 8. And that's going to get us here a number not in scientific notation, too many zeros to count, 3.8 times 10 to the minus 7 molar. Also a reminder that your calculator may not give it to you in scientific notation. Yes, so you don't want to count zeros, put your calculator in scientific notation. Here we want to compare, once again, looking at the H plus to our OH minus concentration. We got minus 7 on our OH minus. We got minus 8 on our H plus. So it is the hydroxide in this case that is larger, and this would be basic. Any questions on that one there? All right, continuing on here for 3 and 4. I guess this one is number 3, I think. So in this case, we have the hydroxide concentration. Doesn't really matter. It's really the same calculation. So we're going to solve for the H plus concentration. Again, will be that constant number of 1 times 10 to the minus 14 divided by the number they gave you. And again, making sure we go exponents. So just a reminder, 1 exponent button, negative button 14, divide 6.2, exponent button, negative button, and a 9. Yeah, and that should be the proper way there to punch that in. And if you do it, obviously if you have the one where you need to put parentheses, do the parentheses. Looks like we will end up with 1.6 times 10 to the minus 6 molar. Again, comparing our H plus to our OH minus. Our H plus is to the minus 6. This is to the minus 9. So the H plus is larger in this case. And that will be an acidic solution because of it. Question on that one there. Okay, and the last one here, this was number 4, I think. Also have the hydroxide concentration, so we're looking for the H plus concentration. So again, H plus here going to be our 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. And looks like a 1.2 times 10 to the minus 12 molar. And comparing our H plus to our OH minus, definitely our H plus is much smaller than our OH minus in this case. And that would mean that this solution would be basic. Any questions on any of those? Again, if you're getting answers, like I said earlier, that the front part looks good, but the exponent part's just slightly off, it's probably how you're punching in. You're hitting something extra you should not be hitting on your calculator. Any questions on those there? All right, let's try another one. What is the hydroxide concentration if the H plus is 2.8 times 10 to the minus 5? And is it acidic, basic, or neutral? So we're really just dividing that to the other side. And that's going to give us 1 times 10 to the minus 14 divided by our H plus, 2.8 times 10 to the minus 5. And we will end up here, again, punching in with our exponent button. And we'll call it 3.6 times 10 to the minus 10 molar. Again, upon comparison, my H plus is to the minus 5 and my OH minus is to the minus 10. That means that the H plus concentration is bigger than the OH minus, and this solution should be acidic. Yeah. Any questions on how to calculate H plus or OH minus concentrations? Pretty straightforward. Only problem people have, like I said, is calculator-based problems. Yes, how to punch it in properly. All right. We're going to skip that one, I think. The next thing we're going to talk about is actually the pH scale. And the pH scale is another way that we measure acidity. And the pH scale runs from 0 to 7 to 14. Less than 7 on the pH scale is acidic. Above 7 is basic. And really, dead on 7 is neutral. And why is dead on 7 neutral? It's because at that point, the H plus concentration equals the OH minus concentration. They both equal 1 times 10 to the minus 7, and that gives you a pH of 7, actually, there on there. 7 is also sort of our center spot there. As you go from 7 heading down to 0, you're becoming more acidic. And as you go from 7 heading to 14, you're becoming more basic. You don't have to worry about that if you don't like logs. Feels too mathy. This is the actual pH formula over here, and it's not negative. That's just from PowerPoint. So that's the actual formula there. This, again, is another formula that we can also see a different way. So the pH is equal to minus the log of the H plus concentration. You may also see it written, the pH is equal to minus the log of the H3O plus. Again, basically same deal between those two. By the way, the pH, it actually tells you in the name what you need to calculate it. You need the H plus concentration, right? So that's why it's called pH, because you need the actual H plus concentration. So speaking of calculators, let's talk about how you should punch these into your calculators, depending on the type of calculator you are using at the time. If you have a display calculator or a non-display calculator, and if you're not sure what type of calculator you have at the moment, all you have to do is hit the log button. And if it says log on your screen, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. So if you hit the log button, it will either say log, display. If it says error, you have a non-display. So if you have a display calculator, you need to punch this formula in just the way it's written. You want to start with the negative button. You then would hit the log button. You then would pipe your number in, making sure you use your exponent button, and then you would hit equals. If you have a non-display calculator, so when you hit log and it says error, you have to work backwards in these formulas. So you have to work this way if you're non-display. Or if you're display, you got to kind of go just the way it's written. So if you have a non-display, you actually need to start with the number. Make sure you use your exponent button. You then need to hit your log button, and then you need to hit your negative button to turn it into a positive number. So again, depending on the calculator that you got rolling, which way you need to go for this equation and a couple others we're going to see in this chapter. So let's talk about the other thing that everybody loves in chemistry, which is significant figures. Yes. So when we talk about significant figures and you're calculating something like pH, your answer when you calculate the pH should have the same number of decimal places as the number of significant figures in the concentration. So it is the number of sig figs in your concentration to decimal places, not significant figures, in your pH value, and vice versa if you're going backwards. So if your concentration has 3 significant figures, your pH should have 3 decimal places, not significant figures, but decimal places. Yeah. So just to make sure everything works on your calculator, give it a go. Calculate the pH here to the proper number of digits. And is it acidic, basic, or neutral? So take a moment there, punch it in whichever way you need to punch it in, and see what you come up with. Take a look a couple of ways. So obviously we're using our pH formula, which once again does tell you what you need. So pH, you need the H plus concentration or the H3O plus. And as I just mentioned before, if you have a display calculator, there it is right there. If you have a display calculator, you're going to go in this direction. And if you have a non-display, you're going to kind of go backwards. So if you're going to punch this in, you got a display calculator, you're going to punch in again the negative button, the log button. You're going to punch 1, you're going to hit your exponent button, your negative button, and 5, and hit equals. If you have a non-display, you're going to start with the numbers. So you can go 1, your exponent button, your negative button, and 5. You then will hit your log button, and then you will hit your negative button one more time. And if you do all of that on your calculator, one of those on your calculator, you should have the lucky number 5 staring at you, hopefully. Yes, and that's what you should have there. All right, that's the first part. Now we want to give the answer to the proper number of digits. So again, should it be 5? Should it be 5.0? Should it be 5.00? Again, the rule is this, which is very commonly misunderstood. I'm going to look at my concentration, and when I look at my concentration, which is this is written in scientific notation, which means this has 2 significant figures. And when I translate that into a pH value, that is not how many significant figures, but it is how many decimal places I should have, which is 2 decimal places. And that means that this is the correct answer. Should be 5.00. Again, 2 significant figures in the concentration gives you 2 decimal places in the pH. Once again, not sig figs to sig figs in this case, yeah? By the way, we will talk about going the other way from pH back to concentration. It works the same way. If you're going from pH back to concentration, you have 2 decimal places. Your concentration should have 2 significant figures. So whichever way you're going, it kind of follows the same rule back and forth. Lastly here, obviously with a pH of 5, that is less than 7, which would tell me I am acidic at this point. Yeah. Any questions on that one there? All right, so let's try some. Okay, so let's take a look. So on the first one here, we have the H plus concentration is 2.1 times 10 to the minus 5. So we could go into our pH equation here, minus the log of the H plus. That's going to give us minus the log of 2.1 times 10 to the minus 5. Again, depending on your calculator, whichever way you need to punch that in, go minus the log. Again, make sure you use your exponent button. 5. Going to get us a 4.68 pH. Once again, in terms of significant figures and all that good stuff, that is 2 sig figs, giving me, again, not 2 significant figures on the answer, but 2 decimal places. Yeah. By the way, first off, any question on the calculation there? Now, obviously, that is, again, a pH that is less than 7, so this should be acidic in this case. Questions on that one there. Now, coming to number 2 here, we have the hydroxide concentration given to us, and we want the pH, which is equal to minus the log of the H plus concentration. Again, that tells you, bless you, exactly what you need to calculate it. That means I need to get myself the H plus concentration, so I could use my KW, my H plus and my OH minus, as we used earlier, 1 times 10 to the minus 14. And if I solve for my H plus, it will equal my 1 times 10 to the minus 14 divided by my OH minus, 5.9 times 10 to the minus 8. And you will end up with, punch the numbers in right there. You might end up with a number. Let's see. And I'll call it 1.7 times 10 to the minus 7 molar. That then is the H plus concentration that can go into here. pH is equal to minus the log of 1.7 times 10 to the minus 7. And if we do that there, looks like a 6.77 pH in this case. And that is also below 7 and is not 7. So it is slightly acidic in this case. We again are going to roll in this class 7 on the nose, or pretty darn super close to 7 for it to be neutral in this case. By the way, the pH here is not 7.23. Now, if you calculate a pH of 7.23 by just throwing this in here and did the pH is equal to minus the log of 5.9 times 10 to the minus 8, you clearly did not calculate the pH because it should be 6.77. But the good news is you did calculate something. So you did use the OH minus concentration. So you did not calculate the pH, but you calculated what is known as the pOH, which maybe not surprisingly enough uses the OH minus concentration. And you will get a, what we got there? 7.23 pOH. Now, why is that maybe not such a bad thing if you calculated it? Maybe not a bad thing if you actually knew you calculated that rather than you thought it was the pH. That is because, as we will see here in a second, there's a nice relationship that the pH plus the pOH equals 14. And that means that you could just take at this point to get the pH would be 14 minus the pOH, which in this case would be 14 minus 7.23, and that will get you your 6.77 pH in this case. So you're just a couple of slides ahead of the place there, but that is definitely not the pH. So just like anything else, it kind of tells you what you need to calculate it. So if you're calculating the pH, you definitely need the H plus concentration or H3O plus. If you're calculating the pOH, which is different than the pH, you need the hydroxide concentration. Any questions on that there? All right. Now, the pH scale is based on the log base 10. So as you move pH by 1, the concentration changes by a factor of 1, basically. So if you have a H plus concentration of 1 times 10 to the minus 3, that's a pH of 3. 1 times 10 to the minus 4 is a pH of 4. 1 times 10 to the minus 5 is a pH of 5. As the H plus concentration increases, there's more H plus in the solution. The pH decreases because the pH, when it gets smaller, is more acidic because you have more H plus floating around. And vice versa, if the H plus concentration decreases, that means the OH minus concentration, because they run opposite of each other, would increase and you would see a larger pH. So remember again that they run opposite of each other. So if you have a larger H plus concentration, you will actually have a lower pH, and vice versa if your hydroxide is larger, you will have a higher pH because of it. Again, it's the free amount of H plus or OH minus that's floating around that solution that has a really big effect on the pH of the solution. Now, there are a couple different ways you can measure pH. One is just using a pH meter, which is right about here. pH meter has an electrode. It measures the H plus concentration in the solution. What does it really do in most cases? Well, it kind of measures voltages. And you calibrate it and go, hey, a voltage of this is like a pH of 4, a voltage of this is a pH of 7, voltage of this is a pH of 10. makes a little calibration curve. And then when you measure your solution, it goes, well, this voltage is here, and you're able to figure out the pH along the way. Yes, sir. Yeah, so they're calibrated pretty well for some of those things. And again, that's why you kind of do a calibration when you use them. And it's based off a lot of times that calibration curve. So that would be taken into account. One of the nice things about the pH meter is it just spits out a number to you. You don't have to sort of guess. We also sometimes will use, like we'll use in lab on Monday or Tuesday of next week, I think, when we do this experiment. We sometimes can use pH paper, and pH paper is basically paper like you dip it in the solution, it changes color. There's like a little color chart, and you try to match up the color as best you can. If you ever like maybe check the pool with the little strip papers, you kind of put it in the water and kind of match up the colors. That's sort of the idea of it. Not as good as a pH meter because obviously it'll just give you kind of a whole number. You got to kind of try to match the color the best you can. We also sometimes will use litmus paper, which does not measure pH, but we use litmus paper sometimes to figure out is the solution acidic or basic. And if we have red litmus paper, and typically if it turns blue or the litmus paper stays blue, that means that the solution is basic. If you have blue litmus paper sometimes and you dip it, it turns red or stays red, it means it's acidic. There's also neutral litmus paper to sometimes use. But again, litmus paper doesn't give you a pH reading or anything like that. It's just very commonly just used to figure out, is this an acidic solution or a basic solution? pH paper will give you a number, and obviously the pH meter will as well. Here is the pH scale, and again, some things as we talked about here: strong base towards the top 14, strong acid towards the bottom there near 1. And then we have some acids there in the acidic. We have pure water there, which is 7. In reality, if you have water that's not pure water, and especially if you leave water kind of sitting out in the open, a lot of times it will pick up some CO2 from the air and make carbonic acid, which typically will actually increase the H plus concentration in it. And people are sometimes surprised when they test their water and it's like way down there in the sort of acidic range. And that's a very common thing that happens. Years ago, when they didn't have such fancy buildings and you were still using the buildings from like the 50s and stuff like that, where it wasn't really sealed really well. A lot of times when you do like a titration experiment like we're going to do tomorrow, a lot of times they will boil the water when they make the sodium hydroxide or something like that to remove the CO2 and bring the pH back close to neutral. Here they have much better venting and stuff like that, so don't worry too much about that anymore. So as we talked about in that last problem, there is definitely similar scales to pH, and one is the POH scale, and we do calculate the POH the same way we really kind of calculate the pH. It is minus the log of the OH minus concentration. By the way, you would punch this in the exact same way you would do pH. So just however you do it, either forward or backwards with your calculator, you would punch it in. Once again, as I mentioned earlier, the name really tells you what you need, POH. You need the OH minus concentration. Just like pH, you need the H plus concentration to do that. And that relationship between the two is the pH plus the POH does equal 14. So it does sort of give you a shortcut that you may not even, like on the previous problem, have to actually use KW. You could, as you saw there, still use KW if you wanted to, but you don't really need to. But you will get the same answer regardless of which one you use. So it does give you a couple of options in terms of how you could get to the answer. You could, like I said, like in that last problem, if you had the OH minus, just get the POH, subtract 14, you got the pH. Or you could do like we did there, where we got the H plus concentration, then put it in. They both will give you the same sort of answer. So in addition to these formulas here, let's talk about how we could kind of go backwards. And what I mean by that is you have the pH, and if the pH is given to you, from the pH, you could actually get the H plus concentration directly from the pH value. And you can get the H plus concentration, it will equal the inverse log of the negative pH. And in addition, if you have the POH given to you, you could get directly from the pOH the OH minus concentration by taking the same calculation, the inverse log of the minus pOH. On most people's calculators, when you hit the inverse log, most people's calculators will pop up a 10 and a caret. You want to make sure it's negative pH. Now, just like the pH formula, depending if you have a display calculator or a non-display calculator, you got to punch it in kind of the same way. So if you have a display calculator, you can punch it in exactly the same as it's written. If you have a non-display, you got to work backwards. Let's talk about a few buttons and what buttons we're talking about. We are talking about when we say inverse log for most people's calculators. Upper left corner of your calculator, there's a shift button, or you may have like a second button up there. And you usually want to hit that plus the log button that has a 10 and an X above it, or how a lot of people used to do scientific notation. So this is actually what you use those buttons for. Now, if you have a display calculator, you would hit the second or the shift button. You would hit the log button. And when you do that, it will probably pop up a 10 and a caret or something like that on your calculator. Then you want to make sure you hit your negative button and then your pH, and you should have something, kind of staring at you, sort of like that. If you have a non-display calculator, you got to go backwards. So you actually need to start with the pH. So you got to pop the pH in there. You then need to make it negative, which means you need to hit the negative button. You then need to hit the shift button or the second button, and then the log button. So you kind of have to go a little backwards in terms of how you hit it. If you do all that, you will end up hopefully with the concentration given to you as you go through it. Any questions on that there? You do got to make sure that they are negative, those values, the pH or the pOH, when they go into there. Now, another really common error that people make is not sure how to punch on any of these into your calculators. So again, make sure you understand how to do the pH versus you're starting with the pH and you want the concentration. Probably the most common error that people make is this. They're asked the question of, is the solution acidic, basic, or neutral? And they're asked that question. And I can't tell you how many quizzes, exams that I've seen over the years where people write, it's acidic. And for the same question and solution, it's basic. I don't think I've ever had anybody go all three. So nobody's done the trifecta of it's acidic, basic, and neutral, the same solution. Cannot be. It is just one answer for that question. So if you're asked, is it acidic, basic, or neutral, you should just put one answer. If you're putting multiple answers, just put an X on it and save me the trouble. Yes. So don't do that. Why do people do that? People do that because in those questions, they're asked to calculate two things. They're asked to calculate the pH and the pOH. And when they do so, they look at the pH value and go, cool, it's less than 7. My solution is acidic. Then they go look at the pOH value and go, cool, it's above 7. Hey, it's basic. And now I have a solution that's both, and that cannot be. Yeah. So my recommendation would be to always look at the pH. You should always probably look at the pH scale. That is because most people have the pH scale in their head. Most people do not have the pOH scale in their head, which runs opposite. So if you have the pH scale, that is 0, 7, 14, less than 7 is acidic, above 7 is basic, and 7 again is neutral. On the pOH scale, it is also 0, 7, and 14, but when you are less than 7, you're basic. When you're above 7, you're acidic. And if you're on 7, you're neutral. They run opposites of each other. If you have a low pH, you will have a high pOH, and vice versa. If you have a high pOH, you will have a low pH. My recommendation is, because most people don't have this scale in their head, never look at the pOH value. I would always look at the pH value, which is typically the value most people have in their head, and just remember